Okay, thank you everybody for being here, whether here in person or on Zoom. At a high level, my PhD research focuses on leveraging the distances, as well as the inherent geometry of problems to remove outliers in GPS, we call fault detection, and also to allow a team of robots to coordinate with each other in order to be able to localize themselves better. By localization, I need to share screen. Thank you, tech team. Is that better? Okay, great. By localization, I mean the ability to figure out where an asset, usually a vehicle or a phone, is located in its surrounding environment. And this is critical for many reasons, whether that's to be able to find victims who are seeking help, to be able to direct your Uber to know where to pick you up, to be able to navigate safely in our crowded airspace or our seas, for precision agriculture, or even to be able to correctly geotag scientific measurements. On a more personal level, let's imagine a simple way that we perform localization maybe in our everyday lives. So say you have a friend out of town visiting here on Stanford campus. They call you up saying that they're lost, their GPS isn't working. So you ask them to describe where they're at. The first thing they tell you is from the bookstore 10 minutes ago. So already in your mind, intuitively, you may be thinking about places that are about a 10 minutes walk from the bookstore. The second thing they tell you is that they can see Hoover Tower about 300 meters away. So in your mind, you do the mix of those two, places that are about 300 meters from Hoover Tower and a 10-minute walk from the bookstore. And then the final piece of information they tell you is that they can see a church about 200 meters away. You know, that's probably you can localize them. You can find their spot on campus to be around the Stanford Oval. And so what you did was you used the combination of both distances they were away from objects, as well as the inherent geometry you know about Stanford campus, where these locations are, in order to be able to find your friend and localize them. And that core idea of utilizing both distances and the underlying geometry PhD. As we saw in that simple example, one distance wasn't enough to be able to find our friend, but the combination of multiple distances can provide rich information for localization. This idea is applicable to a diverse set of settings. And today I will be applies to be able to remove outlier GPS signals, remove these bad GPS signals, as well as navigate on the moon. Okay, so my presentation today will focus on three of my main PhD contributions in this order. In the first part, I'll explain how a tool from graph theory called Euclidean distance matrices allows us to examine the underlying geometry of this GPS localization problem, to be able to both detect and exclude faulty measurements, bad measurements. In the second part, we design a multi-robot coordination algorithm, having robots work together to be able to change their geometry, to be able to provide distance measurements that provide more information to among each other. And then finally, I'll just briefly share about a evaluation framework we created for GNSS datasets and algorithms. These contributions I'm presenting today are just going to be small summaries, but they come from publications that we've had in both conferences and journals. So in terms of fault detection and exclusion, I'll be summarizing work that we've published and submitted to the Journal of Navigation, as well as submitted to conferences, the ION GNSS Plus conference. For the multi-robot coordination, I'll be summarizing work for submission to RAL. And then finally, the evaluation framework we've submitted to Software X Journal, as well as had conference presentations at GNSS Plus as well. And with that, I'll jump into this first contribution of fault detection and exclusion. So today we're talking about geometry, combining geometry and distances And so the distances in this first part of the presentation come from GNSS signals. GNSS is the broader term for not only the United States' GPS constellation, but also Russia's GLONASS, EU's Galileo, et cetera. So this is the broader term for these set of constellations. And how GNSS works is that these satellites send you a timing stamp of when they sent a signal to you. Your receiver, maybe a phone, uses that information, the timing difference between when the signal was sent and when you receive it, to compute this distance we call a pseudo-range between the satellite and the receiver. And using at least 4 of these measurements, your receiver, your phone, is able to compute its 3D position in space, as well as a timing offset between the clocks of the satellite and your phone. And then lastly, I'd like to hit on the fact that these measurements, these distances, are often corrupted by a variety of factors. There's biases in them caused by going through the Earth's atmosphere, caused by reflecting off of objects before they arrive to your receiver, or clocks drifting throughout time. And so you may wonder, do we even care about these biases, these small corruptions? And to answer that, let's return to our simple example. The first thing that our friend told us is that they were walking 10 minutes, that they started walking 10 minutes away ago from the bookstore. Okay, and the assumption we made is that they spent 10 minutes walking directly away from the bookstore. But what if what actually happened is, instead of walking away from the bookstore, they walked to Coupa Cafe, pick up a coffee, and then they started going back towards the direction of the bookstore. In this instance, the distance away from the bookstore is actually much smaller than we previously assumed. And if you see what happens here, using this smaller correct distance away from the bookstore, we actually localize our friend in a completely different location than previously. And so what happened here is that using this bias, this larger than normal measurement, led us to localize in a completely different spot. It turns out that localization, the GPS in our phones only work as well as they do because they're constantly removing these biases. Normally they work really well, but sometimes they don't. If you've ever been in downtown San Francisco or deep in a forest, your phone tells you that you're in a completely different spot than you are. That's because the software in your phone is localizing with some of these bias corrupted measurements. But today, this is a very difficult task, being able to remove all these, because we have many measurements from many different constellations. This graph here is looking up the sky and showing that last Monday, for just over an hour of time, your phone could have listened to 50 satellites. So there's lots of satellites that your phone is able to listen to. And because of this magnitude and number, it is difficult to remove these faults. Although this isn't a new problem. Since the inception of GPS, people have been trying to remove these biases. One of the common ways to remove these biases is called solution separation. In solution separation, you first compute your position estimate using all measurements. And then you compute position estimates using some subsets of those measurements based off of how many biases you think exist. And the idea here is that if you're able to successfully remove all measurements, that your position solution drastically changes, and you're able to detect that change, that there is a fault. However, this can be extremely slow, especially with increasing number of measurements and increasing number of faults hypothesized. So if you're trying to do all possible subsets, this may be trillions of different subsets, depending on how many measurements you have. Another approach, common approach, is to look at the difference between an expected and a measured pseudo-range. So looking at what you'd expect to see versus what you measure. And where that difference is large, you can predict that you should remove those measurements. A third method looks at a 4-dimensional grid of your 3D position and your time offset, and then checks the consistency just along those grid spaces. The downside is that both of these methods, in order to be able to do a good job of removing faults, you also have to have a good job already of estimating your receiver's position. But to be able to have a good job of estimating your receiver's position, you have to have already removed faults. A different way that we propose in this section and our contribution of this part is to remove faults by leveraging Euclidean distance matrices, which I'll define in the next slide. The benefit of this is that by utilizing sort of the properties, the inherent properties of these distances, we're able to not do a combinatorial search, nor have to iterate to be able to converge to an estimate of our receiver's position. Okay, so what is a Euclidean distance matrix? A Euclidean distance matrix is filled with the square distances between all pairs of points in a system. So if we have 4 points, we have this 4x4 matrix. And Euclidean distance matrices have been used for a number of reasons in order to obtain information from distances. They've been used to estimate the shape of rooms using acoustic echoes. They've been able to predict the positions of atoms in a molecule, or more abstractly, be able to figure out the most important trends in high-dimensional data. I think EDMs are extremely beautiful mathematical concept, and if you're interested more about them, I recommend checking out citation 15. What I'll now explain is how, if constructed in a specific manner, these matrices can provide us information about faults in a GNSS scenario, which we introduced in this navigation journal article. Okay, and so what does it mean to have sort of this Euclidean distance matrix in a GNSS scenario? In this example, we have 4 points in our system. We have 3 satellites that our receiver, maybe in a car, is listening to. And so a Euclidean distance matrix in this case is a 4x4 matrix for the 4 points. We start by using the fact that the distance between any point and itself is 0. Then using our measured pseudoranges. So say we measure the distance to these satellites as 3 units. We fill in 3 squared in the appropriate locations. And then to fill in this bottom part of the matrix, we use the known satellite positions. So these satellite positions are known very well and broadcast to us either by the satellites themselves or often cellular networks. So if the satellites are all 1 unit apart, we fill in 1 squared. And there's lots of theory, but I'll just hit on the important part very quickly, is that from this Euclidean distance matrix, we can recover a Gram matrix by some matrix multiplication. Gram matrix is just this matrix with a special form of X transpose X. And the cool part about Gram matrices is that the rank equals the dimensions of the state space. So in this case, we're trying to localize in 3-dimensional space. This matrix has a rank of 3. In non-math terms, this is sort of the idea that we have all these distances that we're trying to fit together like a puzzle. And a rank 3 means that this puzzle is solvable in 3-dimensional space. In 3 dimensions, we can fit all of these distances together. So say that rather than just 3 satellites, we have 20. And we have perfect measurements. So we create this Euclidean distance matrix, this EDM. We recover the Gram matrix, and then we want to know something about its rank. And to do that, one way to do that is to compute its eigenvalues. And so in this plot, we have 3 very large non-zero eigenvalues, and the rest are near 0, which means this matrix is well approximated by a rank 3 matrix. Or that, yeah, this geometry puzzle can fit together in 3-dimensional space. However, something extremely cool happens if we have a bias in this measurement. Because if we have this bias, a fault in our measurements, all of a sudden, the 4th and 5th eigenvalues drastically increase in value. And so what this is sort of saying is that this puzzle of all these distances trying to fit together can no longer happen in a 3-dimensional world, that you would need a 5-dimensional world, whatever that means, to be able to solve this puzzle together. And so this was the case with perfect measurements. We see this very large jump. In reality, our measurements are never perfect, the perfect geometric distance between a receiver and a satellite, that there is We have unmodeled atmospheric effects, biases in our clock, noise in our receiver. This fourth and fifth eigenvalues are usually always above 0. However, when there is a bias, we still see a large jump. You notice this is a log scale between for these fourth and fifth eigenvalues. And so the idea, intuition here is that to be able to detect biases, we can check for this large jump in the fourth and fifth eigenvalue. Okay, so starting from the beginning here is to be able to detect a fault, to detect these biases, maybe a signal hitting off of a building before it comes to us. We use a combination of our measured pseudoranges and our known satellite positions. We construct this EDM with matrix multiplication. We recover a Gram matrix. We calculate its eigenvalues. And then we have this test statistic. So for this test statistic, we average the fourth and fifth eigenvalues. We normalize it by the first, so it's between 0 and 1. And then we check whether or not it's above this threshold. And so this threshold can be set based off of the noise characteristics of our receiver that we normally see. And if it's higher than this threshold, then we detect a fault. If it's lower, then we predict that there are no faults present. What would be nice is if we could know not only do we have a fault, but from what satellite is the faulty measurement? Which one should we remove? To do that, we can look at the eigenvectors of that fourth and fifth eigenvalues. So the idea here is that this fourth and fifth one should be low. But if they have this large increase, what satellite measurement is causing this? So we look at the absolute values of these eigenvectors and remove the largest or these largest absolute value, the satellite corresponding to these largest absolute values. Okay, and so this full algorithm altogether is we use these measurements, we compute our Euclidean distance matrix, recover the Gram matrix with some math, get its eigenvalues, and then what we do is a greedy approach. So we take one step at a time of removing the maximum fault, and then we can repeat this multiple times to be able to remove multiple faults until we fall below this threshold, this decided threshold. And what you see here is that we didn't have to do any subset combinations, nor did we have to take the time to converge to an estimate of our receiver's position. And so we tested this on real-world data. We took this data set from Google, where they have Android phones in the front of their car as they drive around. And they also provided ground truth of exactly where those phones were as they were driving around. What's important here is that there were a large number of measurements. So at each time step, the phone was listening to 25 to 45 different satellites. And so trying to find faults with those across a large number of satellites. And so in real-world data, our real-world data is not perfect. It has biases. And so as an initial step, we condition these pseudoranges so that they're as close as possible to this geometric distance between the receiver and the satellite. And so we remove our modeled atmospheric effects and our clock bias before starting our algorithm. And what we show in this paper is that our method is much faster compared with a comparable greedy residual method. Again, notice the log scale. Both of these methods in theoretical runtime complexity have a n-cubed operation. But the difference here is that the n-cubed operation for residual is having to run multiple times to be able to converge to estimate of our receiver's position, which we don't have to do. For a much more detailed explanation of these time complexities, you can check out our journal article citation 20 here. Okay, so it would be good not just to be fast, but also to be accurate, to be able to properly remove measurements. And so to be able to test that, we use this error metric from literature. where the idea here is that you estimate your position across a range of time steps. You compare it with the ground truth, and then you get all of these points of your error in east, west, north, south. And then a 50% horizontal distance error would be the radius of this circle that encompasses 50% of these errors. So our metrics is this average of 50% and 95%. And what we found is that we're able to have not only be fast, but be comparable in terms of error with the greedy residual method. So what's going on in these plots is that the y-axis here is this error metric. So higher is worse. This top line here is if we always just use all measurements. We have a large amount of error if we just always use all measurements we're given. Slightly below that is if we remove measurements that our Android OS indicate have this fault mode called multipath. And then both our EDM and residual method, based off of the threshold value we choose, which is this x-axis, are able to drastically lower our error metric. So not only are we fast, but with a well-chosen threshold, we're also able to reduce our error. Okay, so in this section, we talked about how we can use these Euclidean distance matrices to be able to understand, be able to leverage this inherent geometry of the GPS localization problem to be able to quickly remove these GPS faults. And with that, we're moving to this second part, the second contribution, where we create an algorithm for robots to be able to coordinate together and localize themselves. So again, presentation, we're talking about geometry and distances. And in this case, we're applying it to this robot swarm. So the algorithm that we propose is applicable to a wide range of robot teams. In this scenario, we focus on these moon rovers due to a collaboration that we have with engineers from NASA JPL that are sending out this cadre team next year. So this is a swarm of little rovers that they're sending out. They have a number of sensors to be able to help localize themselves, figure out where they are on the moon, including cameras, some ranging radios to be able to talk with each other, and a sun sensor to know the angle of the sun. So these robots are going to be driving autonomously. And it's important here that each robot, that planning here is distributed, meaning each robot plans for itself. So it would be undesirable for a single robot to be telling what to do for telling all the other robots what to do. In case this robot has some kind of energy fault or it falls into a crater. So it's important here, as these robots explore, that each one is planning for itself. And to be able to help with that, each robot can communicate some small, due to bandwidth constraints, they can communicate some small amount of information to the other robots. Okay, so how do the robots figure out where they are? Unfortunately, right now, there is no GPS-like constellation for the moon, although several of my colleagues in my lab are doing some exciting work trying to change that. So currently, they often use cameras with feature tracking. So the idea here is that cameras can track features shown in this video of things that stand out in camera images across multiple frames to be able to know how far they've driven, where they're going. However, this method works poorly if there's not like significant things that you can track through these camera frames. And it turns out that the moon is full of locations that are poor for cameras. So this includes sort of like these open fields without rocks, boulders in view of the camera, as well as places that are poorly lit. So the moon has deep shadows. And so if you can't see features in these images, then camera works really poorly. Okay, so if camera is not the answer, what can we do? Say we are this robot and we're trying to traverse up across the moon. So we start out in this location where we in this rock cluster where our camera is working well because we have these things our camera can look at. But if we drive along, we find ourselves in this open plain, our robot can get lost, be able to not know well where it's located. So to be able to fix that, what if we had teammates helping us out, other robots on our team? When we get to this location, this open plain, if the other robots have a good idea of where they are, they're near these rocks, they are able to, their camera is working well. And if we can measure distances between us, then we can use that information about their position and distances to be able to triangulate ourselves in the space. But one catch here is that this works much better depending on the geometry. This works much better if these distances come from a wide range of angles around us. It works poorly if all of these robots are in a straight line. And so our contribution and what we propose in this section is that we need to integrate distances not only in our estimation of figuring out where our robot is located, but also in control. So intelligently deciding what kinds of geometries we should be having for our robot school. Okay, so geometry and distances. Distances in this section come from these things called UWBs, ultra wideband ranging radios. They also work based off of time of flight. And what we want is for these robots to always be communicating distances among each other simultaneously. This is different than how these ranging radios are normally applied. And so thankfully, our colleagues from NASA JPL, they were able to share some software that they developed for those moon rovers that we were able to modify and use on our robots as well, so that all these robots could be communicating with each other at the same time. Okay, so how do these robots independently by themselves figure out where they should go next? And so we start, say our robot is going to be this star in the middle. We start by sampling an option of potential waypoints where we could travel to at our next time step in our immediate vicinity. And then we're going to give them something called a cost function. So for a range of different terms, we're going to give each of these potential spots a cost based off of a variety of factors. So the idea here is at the end, we want to minimize this cost. We want to spend the least amount of money getting to our destination. The first cost here is based off of distance to our goal. So say we're trying to traverse in this direction to the right, the waypoints closer to our goal have lower cost, incentivizing for us to go towards our goal. The next cost here is a collision cost. We don't want to get too close and hit these teammates who are trying to help us out. And so this cost is extremely high as we approach the neighboring robots. And so if our neighboring robots here are stars with their communicated paths here shown in lines, then you can see here that there's a high cost for potential waypoints that approach our neighboring robots. Okay, this third one is slightly more complicated, and this is the geometry aspect. It uses something similar to dilution of precision that we use in GNSS field, but it gives us a measure sort of how good is our geometry. So for an intuitive understanding, if we have 4 robots here, this cost is lowest if we're up here. So if we create sort of this more circular geometry, and it's highest if we're along sort of this straight line with these other robots. So this is incentivizing us to be able to spread out in this more circular way. And so in this example, these are our other robots. And so if we're this star, there's high cost for these going to this position where we'd be in a straight line with these other robots. Okay, so to combine these, we do a weighted sum. And we do this because we don't actually always care about geometry. We only care about geometry if one of the robots on our team is lost, which is this idea of an idea of our uncertainty. So if the maximum uncertainty on our team, if that is high, then we really care about getting good geometry. Otherwise, we should just navigate directly towards our goal. And so we sum all of these, and out of all of our waypoints, we choose to go to this waypoint, we communicate that plan, and start heading there. Okay, to be able to test this algorithm, we had 4 robots traversing across a room, both in simulation and in hardware. And we did this on robots with a very similar sensor suite to the actual moon rovers that are headed to the moon. So they have these ranging radios that can measure distances on top. They have camera, and we use motion capture for our ground truth. Okay, so in these experimental results, we have 2 algorithms that we'll be showing. One is a naive algorithm, where the robots just, they don't care about geometry, they just head directly towards their goals. And versus our proposed algorithm, where we care about this geometry to be able to share better, to be able to have higher information gain for these distance measurements. Okay, so we did this in Stanford Flight Room down in the basement. And so the naive algorithm here, you can see the robots, they don't care about geometry, they just head directly towards the goal. So we're sharing 6 or 7 of these different iterations of these experiments, where best they can, these robots just always head directly towards the other side of the room. Versus our proposed algorithm, what you see here is that as the robots start to traverse, that they form this square to be able to traverse across the room. This is cool because this square is the optimal geometry for 4 robots. That's as close as you can get to a circle for 4 robots is this square shape. And what's also cool is that this is an emergent property, meaning that we didn't specifically command these robots. We didn't tell them you should form a square. This is strictly based off of this cost function. So if you see it, it's actually different robots each time forming like the front of the square versus the back. And why that's also great is that this is agnostic to the number of robots. So if one of these robots has an error, drops into a crater, that the other robots can still communicate with each other, they'd form a triangle. Or if we had 10 robots, that they'd form this larger circle. Yeah, great. Okay, so not only do the robots look cool as they're driving across the flight room, but quantitatively, we have the stop cost and that we quantified and lower compared to this naive algorithm. So here, both in hardware and simulation, we show the mean of the stop cost as well as we shade one sigma on either side of the mean. And not only do we have good geometry, but we showed that because of this good geometry, we're able to decrease our localization error, both the mean and the maximum, because we have better geometry. Okay, so in this section, we introduced this multi-robot coordination algorithm so that robots can create this preferential geometry as they move. And this is because of this like emergent property. Not only does this apply to moon rovers, but this could also apply to other systems that have multiple robots communicating distances, like satellite swarms or maybe even underwater robot teams that can communicate with each other. Okay, so this third section, which will be quick, is this evaluation framework that we created to be able to evaluate GNSS data sets and algorithms. GNSS data comes from a wide range of sources. As you talked about, it comes from lots of different countries. And because of the variety of universities, of researchers, organizations putting out data, all this data is in different forms. And the algorithms as well are extremely difficult to be able to compare against each other. What we found is that frequently, each research team organization created custom code to go between these GNSS data sources and then their algorithms, visualizations, et cetera. And so what we did, team here, is fill that gap with something we call nav data to be able to much more easily go from a wide range of data sources to our algorithms, and do this in a fast way as well. We made this evaluation framework modular, meaning that we can go from a wide range of input sources, whether that's receiver data types, satellite positions, or common GNSS data sets. They can all go into this common form where we transition to a standard naming convention to be able to use downstream, no matter the input source, you're able to make use of the same localization algorithms to be able to compare against each other, as well as visualizations and some core processing utilities to be able to make all of that happen. And what was exciting is that we found that not only was this useful to us here in our lab, but that other people found it interesting. They found it useful as well. So this is open source GNSS libpi. We can only know so much about our users, but what we do know is that we've had thousands of views on GitHub, users from all around the world, as well as I'm proud that it has been integrated into a couple of classes here at Stanford. And with that, today in this presentation, we talked about leveraging the combination of both distance measurements and underlying geometry. In the first part, we used Euclidean distance matrices to gain these insights into the GPS localization geometry to be able to detect and remove faults. Then we created a multi-robot coordination algorithm where these robots created better geometries to be able to gain more information. And then finally, we just hit on briefly this evaluation framework that we made to be able to make this GNSS field more accessible to researchers and scientific users alike. That was, I know, fast, just brief summary. And if you are interested in learning more, I invite you to check out some of our publications. And then just briefly, I'll hit on the fact that these EDMs could be, I think, very useful in a machine learning approach where you can use as features these eigenvalues and eigenvectors. I think it would also be interesting to apply to this natural four-dimensional problem of the added time for these EDMs. And then also there's a variety of other ways that we could combine both camera and our distance measurements. Okay, and with that, I'd like to, very grateful for funding both from NASA, JPL, and NSF. I'd like to thank all of my defense committee members for being here, for providing feedback, for great interactions at conferences over the years. I especially thank my advisor, Professor Grace Gao, for 5 years of very helpful, excellent advice. And none of this would have been possible without my stellar lab mates in the nav lab, providing advice and camaraderie, and my lovely family. And with that, have time for a couple questions.